So, shall we make a start? The last session, we get less and less people. So, welcome to the last session of the third workshop in methodologies for official statistics. And I particularly want to thank Maro and the whole Istat team for hosting these fabulous, what is now the third workshop. And I hope there'll be many more. And so this session is in collaboration with the International Association of Survey Statisticians. And the topic is on new data sources for official statistics. I just wanted to take 5 minutes. I don't want to take away too much time from Jan's presentation, but just a few minutes about the International Association of Survey Statisticians. I'm the current president. Monica Portizzi was the past president. So we have a lot of people in Istat that are members of the association. And it's a network of professionals where we engage in survey research, particularly as a professional society, to make sure ethical standards are held, best practices, mutual sharing of information. So our objectives are to promote the study and development of the theory and practice of sample surveys and censuses, and to make sure we have an increase in interest in surveys and statistics and censuses among statisticians, governments, and the public, and to promote, particularly in this era of data digitalization, the modern data ecosystem, providing new data sources, including non-probability surveys, which aim to provide granular data, which is more timely perhaps than our surveys and censuses, and to promote the modernization of national statistical systems through the interoperability of data sources. And to achieve these objectives, one way we do that is to engage in these fantastic regional conferences. We just got back from Canada, where we're at the Methodology Symposium, also hosting a session there. So if you have any workshops or conferences coming up, please keep in mind that we like to increase our visibility and to host sessions at conferences. So other activities besides showing up at conferences is just to let you know, and I have websites here as well. You can take a look. We have our journal, which is called the Survey Statistician. We issue it twice a year. And it includes country reports, which is really interesting because every country has a representative who writes to us about what's happening in their countries. We also have sections on new and emerging methods where we get leading statisticians to talk about some new methods. We have an Ask the Experts. We have a section now on young survey statistician with Veronica as our current editor of that, our book reviews, etc. We also have short courses prior to each ISI conference. We have a dedicated website and newsletters, and most like a really important way that we improve our capacity building, if you will, is through our webinar series. So we have monthly webinar series with distinguished speakers on the theory and practice of surveys and censuses. We offer conference support and like to actually engage in conferences as well related to survey statistics. And I want to highlight that this is open now. We have the Cochrane-Hanson Prize. So it's awarded every 2 years, and now we're in 2025, and it's awarded for the best paper on survey research methods submitted by a young statistician from a developing country. So those of you who are engaged in, say, academic research and have a PhD student who might qualify for this prize, please keep it in mind and nominate that student. And then every other year we have the Hukum Chandra Memorial Prize, which was actually just last October, we had the webinar dedicated to the prize winner, who was Nicola Salvati from Pisa. So well done to Nicola. So that's awarded every 2 years to sort of a mid-career researcher. And we don't get a lot of younger people engaged in professional societies. And I just wanted to say that professional societies play a pivotal role in the shaping of new strategies for statistical systems. And it's incredibly important to be engaged and to join a professional society. The success, development, and growth of official statistics is fundamental to professional statisticians as producers and users, and also to engage with quality assurance of these statistics statistics. And our role as a professional society is also to ensure the leadership, statistical capacity building, collaborating on ethics and codes of practice, equality frameworks, maintaining confidence in new systems, including through data governance, et cetera, and providing support for innovation. And so it's really, important. I know young people say, oh, why do I need to join a professional society? But they are really important. And so why are we focusing on this session on new data sources and small area estimation or official statistics? So the NSIs, of course, are under increasing pressure to reduce costs and response burden. And obviously, as you've seen in the last day or so, is that there's a big investigation of alternative non-survey data sources to integrate with survey data. And we can do that indirectly through small area estimation or more directly trying to build statistical registers, mass imputation. We heard a lot about that in the last few days. What that means is that there's more reliance on models to compensate for selection bias, measurement errors, model-based inferences, which are assumptions that may be hard to verify. And so all papers in this session focus on model-based inference, so with applications of smaller estimation or time series. I think Jan is going to touch on that. Using new sources of data, administrative data or web scrape data. So that's the focus of this session. And we're addressing real problems in the production of official statistics. So I hope you engage with the session. And the future of national statistical systems rely more on these new data sources and data integration. And what that means for our national statistical systems is that there's a need for more acceptance of model-based estimation, which is slow to come in the NSIs, and also looking at more applications of data integration and small area estimation, particularly using new data sources. And they should sort of move from this experimental statistics, if you will, to more the mainline official statistics. So this is what's coming. But at the same time, we need to address the criticisms by government and policymakers to adapt changes in official statistics. And just recently, there's been a lot of media attention on the Office for National Statistics, where the article states that the UK has a fundamental breakdown in the reliability of data. And one of the reasons is, of course, their move towards administrative sources. So you can't move too fast. You have to make sure that your clients are on board to these new methodologies, and it's really important. So there's a big backlash now in the ONS. So what happened to your migration statistics are now trying to rely solely on administrative data versus the previous method, which was using survey data. And they have big problems with their labor force survey that's undergoing transitions now. I think they had like a 13% response rate on their last survey. So they're really, but it sort of highlighted that, okay, we need to be innovative. We need to move to, move from experimental to official statistics, all these model-based inferences and new data sources. But at the same time, we do need to take care with that our clients are on board. And a big worry, of course, is what happens if that data all of a sudden that you're relying on is discontinued in some way. And so that's another issue in terms of contingency plans. What happens if the access is stopped? So there is a lot of challenges in this new paradigm. So introduction of the papers, we're going to start with the master class, new data sources and inference methods for official statistics. And we're delighted to have Jan van den Broek with us from CBS Netherlands. I'm going to have your bio, which I'll read. Professor Jan van den Broek obtained his MSc in biometrics starting at the Methodology Department of Statistics Netherlands back in 1994. In 2001, he obtained a PhD in design-based inference methods for the analysis of large-scale field experiments embedded in probability samples. I think that was the only PhD I've seen on that topic. It's really a great topic. Since 2010, he has also a position at the Department of Quantitative Economics at Maastricht University. His research interests are sampling theory, design, and analysis of experiments, time series analysis, and small error estimation. So we're delighted that you can give our master class. After the break, we have two papers, and Giovanna will be the discussant. So the first paper is on official statistics, Bayesian small area estimation of origin destination matrix. And the second paper, controlling selection bias in non-probability samples using small area estimation, an application to official statistics. So give you a second while we change the slides to go use your QR codes to go on and become a member of the International Association of Survey Statisticians. It's only 60 euros a year. So, and it supports a lot of really good activities. Thank you.
Thank you. I can get rid of it. Okay, good afternoon. Thanks, Natalie, for the nice introduction and for inviting me for this presentation here. Apologize that I put off my jacket, but it's terribly hot inside for me here. So before I faint, I took it out. So the purpose of this presentation is to give a kind of an overview of different methods, how to use different methods, how to use new data sources for the production of official statistics. And with new data sources, I mean any kind of data sources that are not based on probability sampling. So it can be big data, non-probability data. And I will try to illustrate this with some applications that we have done or are currently doing at Statistics Netherlands. Nothing happens.
This doesn't
work.
Yes, it does.
So this is an outline of the paper. I will start with an introduction, and in this paper I roughly distinguish three ways of using new data sources in the production of official statistics. The first approach is to use the non-probability data of new data as the primary data source. I will only talk briefly about that because that is not the topic of this session. The main part of the presentation will be the second approach, using non-probability data as covariates in model-based inference methods. And I will illustrate that with a time series model that we already have in production in the Netherlands to produce monthly labor force statistics. I also present some results of an ongoing project where we try to predict poverty from aerial images. And the third approach is basically to use machine learning to retrieve statistical information from a non-probability sample and use that as auxiliary information to improve the sampling strategy in just our familiar design-based context. And I will wrap up with a discussion. So official statistics are traditionally based on probability sampling in combination with design-based or model-assisted inference. And that is very popular in national statistical institutes because of the following advantages. This approach is robust for model misspecification. And under this approach, we work with design data, which implies that you have control over the precision of your statistical output by variance calculation and minimum sample size calculation. But we're also in complete control over the availability of the data and the stability and the comparability of the data over time, which is an important aspect for data users. And finally, we're in control over the operationalization of concepts in the way how we implement the variables that we want to measure in the questionnaire. And all these aspects implies that under this approach we have a relatively low risk of impairment under this approach. But there are, of course, also disadvantages with survey sample data. Data collection is expensive. The whole process is not very timely. In the case of very detailed breakdowns, you have small sample sizes, and that results under this approach in unacceptable high variances. The validity of the outcomes is more and more compromised by slightly increasing non-response. And finally, conducting sample surveys increases response burden, which is particularly an issue in business surveys. So national statistical institutes have also an increasing interest in alternative data sources. And examples are time and location of network activities available for mobile phone companies, social media messages, internet search behavior from Google Trends, sensor data that comes from satellite or aerial images, or just administrative data from tax registers. And some strong points of non-probability data is that it can come in large amounts of records. Data collection can be cost effective. Sometimes it comes in high frequencies, which enables you to make estimates in real time, sometimes called nowcasting. And yeah, these large amounts of records also help you to make detailed statistics. And in some cases, the data measure directly the behavior of people. And instead of asking people about their behavior, this might reduce the measurement bias at the individual level. But there are, of course, weak points. Non-probability data, we have the main issue is the selection bias with respect to the target population to which the results have to be generalized to. I'm now looking at Professor Tillet, who was very, I must be careful what I exactly mean with selection bias, understood from your presentation. Another problem is that most of these data are unstructured in the sense that it is difficult to distinguish the units in the population where you want to make inference about. Most of the time, these data sources do not have or only have 4 auxiliary variables that you need to correct for selection bias. And in many cases, you have to work or you have to accept a suboptimal construct of the intended target variable. And finally, using this data implies a higher risk appetite. Because you have no design phase that gives you control over the required accuracy. You need model-based inference methods to correct for selection bias. And above all, you have no control over the availability of the data source. Also, you have no control over the stability and the consistency of the data sources over time. So the question is, how can we use these data in a nice way in the production of official statistics? And as I already said, I distinguish 3 different ways. You can use them as a primary data source, or you use them as covariates in the model-based estimation procedure, or you use the auxiliary information just to improve the sample strategy in the familiar design-based context. Now, briefly starting with the first, using non-probability data as a primary data source. The main issue is, selection bias with respect to the intended target population. And this has been nicely illustrated by the famous paper of Meng. He showed that the estimation error of any kind of data set is just the product of these three components. It's the product of the correlation between your target variable and the response indicator, the amount of available data, and the dispersion of the data in your data set. And the point of this paper is that you need random selection to ensure that this correlation is equal to 0. And he nicely illustrates that small deviations of this correlation can result in very large biases. And he showed, for example, that in the case of a sample of 2.3 billion units, a correlation of, that seems to be relatively small, reduces the accuracy of this large big data set, to the level of uncertainty that you would also obtain with a simple random sample of only 400 units. Nevertheless, using non-probability data becomes more and more important, as we have seen in the previous presentations. There is a lot of literature, growing literature on the bias correction methods in non-probability samples. If your data selection process is non-informative, you can do the traditional weighting. But if that's not the case, we learned yesterday from Danny Pfefferman that we can use informative sampling. There are also other methods that use some kind of reference sample that is based on a probability sample to, for example, explicitly model the inclusion probabilities. Or you can apply what's sometimes referred to as a superpopulation model to predict the variables that are not included in the sample. And again, there is a lot of literature on this topic, and a few nice overview. Thank you. Overview papers are the paper by Rao, but also from Changbao Wu. Now, the main issues with using big data as a primary data source is that the methods to correct for selection bias, they always assume structured data, which means that you must be able to identify the units of the target population also in your non-probability data source. And these methods also assume the availability of strongly correlated auxiliary information. And that basically implies that this aforementioned literature can be used to correct for example, opt-in samples or surveys that are based on non-probability samples, but other big data sources often do not meet these requirements. So the question is this appropriate for official statistics? Well, you have to make strong assumptions. Most methods that are currently available still assume that data are missing at random. You have no control, again, over the availability of the data source, and also not about the comparability and the stability over time of the data source. So this requires a much higher risk appetite for a National Statistical Institute to use this type of data. But instead of claiming that the glass is half empty, you can also say it's half full. There are successful applications. Different National Statistical Institutes use scanner data for measuring price indices. In the Netherlands, income statistics are completely compiled from tax and social benefit registers. And also a part of our business statistics comes from value-added tax registers. And we're also busy with retrieving statistical information from aerial images to measure, for example, land use. But the main topic of this session is on small area estimation and model-based inference. So let's move now to the use of non-probability data as covariates in model-based inference approaches. The relevance of statistical information for data users or policymakers increases with the level of detail its timeliness, and its frequency, and also its comparability over time. Monthly figures are, for data users, much more informative than annual figures. And figures on the municipal level are more informative or more useful than figures on the national level. But making very refined estimates on a very refined detail result in very small sample sizes. And also making very timely estimates requires that you have a high frequency, and that implies a small reference period, and that also limits the amount of available data. And yeah, the standard design-based methods imply unacceptable large variances under small sample sizes. But there is a lot of literature that is based on model-based inference procedures that deal with these problems. There is a lot of literature on small area estimation to make more precise estimates at very detailed levels. And there's also a lot of literature for about nowcasting to make more timely estimates. And the potential way to use these new data sources is to use them as covariates in small area estimation models or nowcasting models. And it helps, sorry. That allows you to use, for example, the high frequency of these data sources to produce more timely nowcasts. Well, this is of course not my own, this is not my idea. And maybe one of the early papers on using non-probability data as auxiliary information in small area estimation models is the paper by Marchetti et al. But yesterday there was also a paper by Tioto, who applied also information from GPS trackers as a covariate for area level models. In the context of small domain estimation for poverty data, there is a lot of literature. But most of these models are based on cross-sectional models that allow you to use statistical information from other domains observed in the same reference period to make more precise predictions. But most official statistics are based on repeated surveys. So it's also efficient to use the sample information from previous reference periods to make more precise estimates. So time series models could also be a very potential way to produce model-based official statistics. This allows you to use sample information not only from previous periods, but also from other domains by modeling temporal and cross-sectional correlations. And this approach can be extended by combining them with auxiliary series that are derived from big data sources that further improve the precision. But again, the higher frequency of these data sources can also be used to make estimates in real time, sometimes called nowcasting. And now I will proceed by illustrate this with an example from the Dutch Labor Force Survey. We have already a structural time series model in production to produce monthly labor force figures. And now I like to illustrate how we can extend this model with, for example, claimant counts that are the number of people that receive unemployment benefits from a register, or for example, Google Trends. But standard models assume that the relations are time invariant. So I will also show some results from a project where we extend this model to a model where we allow for time variant correlations. So this is some joint work with other colleagues from Statistics Netherlands and university. I start with the introduction of the model that we have in place for our Dutch Labor Force Survey. The Dutch Labor Force Survey is based on a rotating panel design. Each month, we draw a new sample that enters the panel, and that panel is observed 5 times at quarterly intervals. Data collection in the first wave is based on a mixed mode design, and in the follow-up waves with telephone interviewing only. And in general, inference is based on the general regression estimator. And there are some problems with this setup. First of all, the sample size is too small to produce monthly figures with a direct estimator like the Greg estimator. And in the past, we used rolling quarterly figures as an alternative. Another issue with rotating panel designs is rotation group bias, which refers to the phenomena that there are systematic differences in the outcomes between the observations in the subsequent waves of the rotating panel. It's illustrated with this figure. In blue, you see the estimates for the total unemployment in the Netherlands based on the first wave. And in red, you see the same estimates that are based on the 4 follow-up waves. And you see a systematic difference, and that is a general issue with rotating panel designs, which is known as rotation group bias. And yeah, over time, our survey is redesigned different times, and that results big shocks in the outcomes. That's called discontinuities. And one way to handle with all these problems is to use a multivariate state space model that is originally proposed by Danny Pfefferman. We use that as a form of small area estimation to borrow strength over time, or to use sample information from previous periods to make more precise predictions for the last period. But we also use it to account for rotation group bias, to model the serial correlation because of the panel overlap, to model the shocks due to the survey redesigns. And yeah, the topic for today is to show how you can extend this model with auxiliary series that come from non-probability data. Now, first introducing the model. The rotation scheme implies that we collect each month data in 5 independent samples. So if y hat, subscript t, and superscript j denote the Greg estimate, that is form of month t, that is based on the panel that is observed for the jth time. Yeah, then we have each month we observe 5 Greg estimates. Yeah? So the first one is the Greg estimate based on the sample that entered the panel for the first in period t, and that is observed for the first time. But each month we also collect data, and we can make an estimate, the second one, that is based on the sample that entered the panel 3 months ago, and it is observed for the second time. So we have also y superscript 3, that entered the panel 6 months ago and is observed for the third time, until y superscript 5, that is the sample that entered the panel a year ago, is observed for the 5th time, and then leaves the rotating panel design. Now this gives rise to a 5-dimensional time series that can be modeled in the following way. The model contains, it's a state space model. It contains, in this space, 3 components. The first component basically states that these 5 Greg estimates are 5 independent estimates for the unknown population total, theta t. And that is modeled on its turn with a structural time series model that contains a stochastic trend and a stochastic seasonal component and a population white noise for the unexplained variation. For this paper, the details of the trend component are important. So I specify here the trend component that we use. We use, if you are familiar with state space modeling, the smooth trend model. That implies that the level in period t is just the level of the previous period plus some period-to-period change. You can see it as a slope. And this slope is modeled with a random walk. And yeah, it is actually this random term, this eta t, that makes the model so flexible that it can gradually adapt to the average level of the series. Therefore, it's sometimes also called the trend cycle model. And it is actually the flexibility of the variance of this slope disturbance terms that defines the flexibility of the trend. Well, we have a similar dynamic model for the seasonal component, but these details I don't need. Now, the second component models the rotation group bias. To identify this component, we assume that the observations in the first wave are the most reliable one, that they are unbiased. And then the other lambdas here are just random walks, specified here, that measures the systematic difference between the follow-up waves with respect to the first wave. And by doing so, we basically benchmark the estimates of the population parameter to the level of the first wave. The third component models the sampling error, and here we account for heteroscedasticity. We do that by scaling the sampling errors with the standard error of the input series. So these standard errors here are obtained from the microdata and used in the model as being fixed or known in advance. And these scaled sampling errors are made stationary in this way. And the first wave that is observed for the first time is not correlated with any information from the past, so it's assumed to come from a normal distribution. But the follow-up waves, they are correlated with sampling errors from previous periods. For example, in general, you can say the sampling error of the wave J in period T is based on the same sample information of the sample from wave G-1 3 months ago, and we modeled this correlation with an AR3 model that for which the autocorrelation coefficients for the first and second leg are put to 0, and we only have a correlation for the third leg that is also calculated from the microdata. Now, these models can be estimated in state space form, which implies that you have an observation equation that states how the observed 5-dimensional series depends on a vector of unknown state variables. So this is a vector alpha that contains the components for the labels for the trend and the seasonal and rotation group bias, etc. But there is also a state equation that states how the states from period T-1 evolve to the period T. And once you have it in this state space form, you can apply a recursive algorithm that is known as the Kalman filter to get optimal estimates for all the state variables. Now, we implemented this somewhere in 2010, and we use this to produce official monthly labor force figures for the unemployed labor force, the employed labor force, the total labor force. And each month we do that at the national level, but also for a breakdown in 6 domains that is based on gender and age in 3 classes. And here you see some results. So the tiny dashed lines that are the input series based on the 5 waves, so that are the time series of the Greg estimates for the 5 different waves, which is the input for the time series model. And in black, you see the filtered trend that we obtain with the model just presented. Now here we compare the unemployed labor force at the national level with the rolling quarterly figure that we had in place in the past. It's the blue dashed line. And we compare it with the filtered estimates for the signal, which is defined as the trend plus the seasonal component. So you see that these real monthly figures have a more explicit seasonal pattern. And they also have the advantage that they are more timely, because a rolling quarterly figure comes unnecessarily 1 month later, because the reference period is the mid-month of the rolling quarter. Now here you see the standard errors. The solid black line are the standard errors of the monthly figures based on the Greg estimator. The broken line here in the middle, that are the standard errors based for the signal, based on the time series model just presented. So the difference between the solid line and this broken line is the increase in precision, because you use sample information from previous periods with this time series model. Now, some possible extensions. One way to improve the estimates is not to apply this MOS model to each domain separately, but combine the 6 domains in a 30-dimensional state space model that allows you not only to use sample information from previous periods, but also cross-sectional information from the different domains. But you can also extend it with auxiliary information that comes from claimant count register or from Google Trends. Now, starting with a 30-dimensional model for the 6 domains, we can easily stack the 5-dimensional time series upon each other, and that gives you an input series of 30 time series. And they all have their own population parameter, their own rotation group bias component, and their own sampling error component. And these times of the filtered estimates for the trend and the population parameter can benefit from the sample information from the other domains by modeling the correlation between the slope disturbance terms of the trend. So this is again the time series model that we use for the trend, the smooth trend model. And we can, for example, model the correlation between these 6 slope disturbance terms in a 6-dimensional covariance matrix. And if you look at the maximum likelihood estimates for these correlations, you see indeed that there is a strong positive correlation between the unemployment figures of these 6 different domains. Another way, and that is basically the purpose of this paper, is to show how you can make use of auxiliary information. Now, the black lines are again the input series based on the 5 different panels, the GREC estimates at the national level. And in red, you see the series that comes from our claimant count register. So these are the people that receive unemployment benefits. And it really follows the same evolution as our labor force survey, naturally. And one way to take advantage of this is to include this auxiliary series as an additional series in your input, in the input factor. And now we have a population parameter for our labor force indicator and another one for this claimant count indicator. And they have their own, they both have their own trend level and their own seasonal component and their own population disturbance term. And similarly as before, we can model the correlation between the slope disturbance terms of the labor force indicator and our claimant count indicator. And that implies a covariance structure for slope disturbance terms that's specified here. Oops. And in this case, also we observe a strong correlation that is larger than 90%. In this graph, you see the standard errors for the unemployed labor force, in this case for the domain of men at an age of 25 between 44 years. In blue, you see the standard errors of the GREC estimates for the monthly series. In red, you see the standard error that is based on the production model that only uses the sample data, but no auxiliary information or information from other domains. In black, you see the standard errors of the 30-dimensional state space model that combines the 6 domains in one model. And in yellow, you see the standard errors that is based on a 6-dimensional model that only use the labor force data for this particular domain in combination with the claimant count series. So the difference between blue and red is the increase in precision because you use sample information from the past. The difference between red and black is the additional improvement in precision because you also borrow strength over the different domains, the cross-sectional correlations. And the difference between red and yellow, that is basically additional information that comes from the claimant counts. Now, if you think in terms of using big data, you could consider to extend this model with the claimant counts, also with a bench of Google trends that are based on search terms which are related to unemployment. Here in black, you see again the input series of our labor force survey, the Greg estimates based on the 5 different panels. Now in green, you see the claimant counts. In the previous example, it was in red. And in red, you see a Google trend that is based on the search term job description. And again, you see that it has a similar pattern as our labor force series. So yeah, the question is, can we also use this additional information? And the nice thing of Google Trends is that it comes in a high frequency. So with this information, you could potentially improve the accuracy and the time as well as timeliness. But the issue is that it's not so difficult to come up with a huge amount of potential series. And in this case, we could define 80 series that is related to unemployment. And you cannot just extend that state space model with 80 series and allow a full covariance matrix of 80 by 80. That results in high dimensionality problems. So the solution here is to use a dynamic factor model, which is fitted in a 2-step estimator. And that is also not my idea. That comes from a paper from Gianon et al. And yeah, the first step is to estimate the common factors in the Google Trends with some principal component analysis approach. So here, the bold X denote a vector that contains these 80 Google Trends. The delta is, let's start with the F. The F contains a vector of dimension R, which contains the common factors. And yeah, this number of common factors is much, much smaller than the observed number of Google Trends. To apply principal component analysis to time series analysis, yeah, you must assume or you must verify that you use series that have an order of integration that does not exceed 1. So we assume this model for the common factors. The delta contains an n times r matrix with the factor loadings. The epsilon is a vector that contains the individual shocks in the Google Trends. And yeah, the bold psi is just the variance of this idiosyncratic components. And to identify the model, we standardize the input series, and that allows us to assume that the covariance matrix of the level disturbance terms of the factor loadings is an identity matrix. Now, F, delta, and psi are estimated with principal component analysis. And in the second step, we extend our model with these 80 Google Trends, which follow this dynamic factor model here. And in a similar way, as already explained before, we can model the correlation between the slope disturbance terms of our labor force survey, is L, with the level disturbance terms from the common factors of the Google Trends, but also for the slope disturbance terms of the trend component of the claimant counts, resulting in this covariance matrix. Yeah, with the comma filter, we refit the comma factors, but we use the comma factor loadings and this covariance matrix in the model as we obtained it in the first step and keep it fixed. Now, to show some results, we have 4 models. We have a production model that does not contain auxiliary series. We can extend it with the claimant counts. We can also extend it with the Google Trends, or we can combine them with claimant counts and Google Trends. We apply these 4 models to a period of January 2004 until the end of 2017. We look at the estimation accuracy by taking the average of the mean squared errors of the filtered estimates over the last 4 years. We also look at the nowcast accuracy by looking at the one step ahead prediction errors, or the mean squared forecast errors, over the last 4 years. And in this forecasting exercise, we assume that we do not have the labor force estimates for period T, also not the claimant counts for period T, but only the Google Trends, because they come in time. Here you see the maximum likelihood estimates for the correlations between the slope disturbance terms of our labor force indicator and the claimant counts, the Google Trends, and also in the combined model. For the Google Trends, we use the first 2 comma factors. In the table, you see the point estimates, the maximum likelihood estimates, and between brackets, you see the p-value of the likelihood ratio test on the hypothesis that this correlation is equal to 0. Now, for the model that is extended with the claimant counts only, we see a strong correlation of 0.92. For the Google Trends, we also see correlations that are significantly different from 0. And if you combine them, the correlation reduces a bit, but it remains sustainable. Here you see the mean squared errors and the mean squared forecast errors for the different models for the trend and also for the signal, which is the trend plus the seasonal. And we present it here relatively to the production model. So values smaller than 1 imply an improvement in precision. And you see, for example, for the trend, that the mean squared error of the filtered trends, they are reduced with 14% if you use claimant counts, also with 40% if you use the Google Trends, and 15% if you combine the claimant counts with the Google Trends. For the mean squared forecast error, you see that the claimant counts are a bit stronger or better to use than the Google Trends. Here the mean squared forecast error is somewhat higher compared to with the Google Trends compared to the claimant counts. And you see basically the same pattern for the signal. You see a reduction for the mean squared error of 12%, 11%. For the mean squared forecast error, the claimant counts do clearly better than the Google Trends. So to summarize, with the claimant counts, they have a strong correlation with the labor force survey statistics. They improve the estimates, but also the nowcasts. And compared to the Google Trends, it is a relatively simple model. For the Google Trends, we use 2 common factors that also have strong correlations with the labor force survey. They improve the estimates, also the nowcasts, but the claimant counts outperform the Google Trends in terms of nowcasting. Well, I think for the Netherlands, it's not worthwhile to use this very complex model, but for countries that doesn't have a register on claimant counts, it might be worthwhile. Now I want to go back to the state space model that we use for production and extended with the claimant counts. This is the model that I presented before. And we make here a strong assumption that the correlation between the slope disturbance terms of the labor force series and the claimant counts is time invariant. So we have here a time invariant correlation. And that can be a strong assumption because relationships between the labor force survey and claimant counts change over time. For example, because of legislative changes concerning people who are qualified to receive this unemployment benefits, but also because of the global financial crisis in 2008. In the Netherlands, people can receive unemployment benefits for a maximum of 2 years. It can be shorter. That depends on the history, on the period that you have worked. But we observed that the long-term unemployment as a result of the crisis is not picked up by the claimant counts, because people that remain unemployed longer than 2 years, they leave the claimant count register. And that is what you see here. So in the first period, you see a strong correlation between the labor force series and the claimant counts. Now, this is 2008. This is the start of the global financial crisis. And 2 years later, you see indeed that the relationship between the claimant counts and our labor force survey deteriorates. And it takes a few years before it is restored again. So in another project, we propose a state space model that allows for time-varying correlations. So we make a very small notational adjustment here by putting a subscript D under the correlation component, but that has very large methodological consequences. So in another project, we considered 2 specifications for a time-varying correlation. The first one was a deterministic specification that is based on cubic splines. And this has the advantage that the state space model remains linear and that we can still estimate these models with a Kalman filter. But the uncertainty under the cubic splines at the end of the series is extremely high, so this is not really an appropriate approach. And therefore, we also developed another method that is based on a stochastic specification of the time-varying correlations. But that has the disadvantage that the state space model becomes nonlinear. And we propose an estimation procedure that proceeds with what is known as indirect inference, using the cubic splines from the first approach as an auxiliary model. But this is followed up by a particle filter that is based on a raw black-localized bootstrap filter. Now, starting with the first approach, the cubic splines. To keep the correlations in their admissible range of -1 and 1, we make a transformation that is based on the tangens hyperbolicus. And then we model these transferred correlations with the cubic splines, where the bold W are the splines weights, and the theta are the coefficients which we also estimate with maximum likelihood. And this is similar as that we estimate the other hyperparameters of the state space model with maximum likelihood. We assume for the Kalman filter that they are known in advance, and that has the advantage that this gamma is known, and we can still apply the standard Kalman filter, which is computationally fast. But the disadvantage is mainly that at the end of the series, these splines are extremely uncertain. And the whole idea of using this state space model is to make more precise estimates for the last observation in the time series. So the second approach that is based on a stochastic specification of the transformed correlations. And we model here the correlations with a random walk. And we treat this as an additional state variable. And this makes the state space model nonlinear, because we have this correlation here in our state factor, but it is also directly included here in the covariance matrix of the transition equation. And under this model, the likelihood function is not traceable anymore, and you cannot apply the Kalman filter. So what we developed here is we estimate the variance of the correlation disturbance terms, these zetas, by using an indirect inference method that is based on the cubic spline model as an auxiliary model. And then we estimate the state variables. Once we have an estimate for this variance for the correlation how it changes over time, then we can estimate the state variables with a particle filter. And we basically apply here also a raw black-localized bootstrap filter. Here you see some results. you see the estimated correlations under 3 models. In blue, you see the estimate that is based on a model that assumes that the correlation is constant in time. In red, you see the estimates that is based on the cubic splines. And in black, you see the raw black-wise bootstrap filter estimates. And this gray vertical bar here, that is basically the start of the global financial crisis. Both the cubic splines and the raw black-wise bootstrap filter, they observe the deterioration of the correlation in the period after the financial crisis. But under the model that assumes a constant correlation, in this period, the model is totally misspecified. Well, here you see 95% confidence intervals for the correlation estimates under the splines. You see that in the period that the correlation changes, the uncertainty is extremely high, but also at the end of the series. And it makes a strange drop here, which is not explainable. Our raw black-wise bootstrap filter also observes the deterioration during the period after the global financial crisis, but it remains high at the end of the series. Now here you see filtered estimates for the trend based on the 3 different models, using the series that is observed from 2005 until the end of 2019. Well, you see small differences under the model that assumes a constant correlation. That is basically because of we call it a large scale or a small scale, I don't know, but the scale of the Y series, but also because of that we use the entire series here. In a moment, I will also show estimates in real time, and then the bias under the misspecified model is larger. That's the wrong. Here we plot the variance of the filter trend. You see, for example, the variance under the model that assumes a constant correlation. It is misspecified in this period, and it underestimates the uncertainty of our filtered estimates, trend estimates. Another thing that you see, for example, in red with the cubic splines, they have an unnecessary large variance at the end because the estimate for the correlation for some unknown reason drops at the end of the series because the uncertainty under a cubic spline model is very large at the end of the series. And this basically makes the cubic spline approach not applicable for our model. As I said, we look here at the constant correlation estimates in real time. So in this graph, you see estimates for the correlation under the model with constant correlations. Well, you see that in 2010, 2011, 12, and 13, the estimated correlation is still increasing. It doesn't observe any change, negative change or drop in the correlation. Only in 2014, the correlation estimate drops to still a high level of 0.85. Now, if you look at the trend estimates in real time, using, for example, the data observed until 2012, I now compare the filtered trend under the model with a constant correlation in blue, with the raw black-wise filter in black, and with the model that doesn't use claimant counts at all in green. And I'm not claiming that this is a good benchmark, but you see that there is a large difference between the green model and the blue model, and that is basically because we think there is an additional bias in the model that assumes a constant correlation in this period where it is really misspecified. How much time do I have? Okay. Another project that is ongoing is that we try to predict poverty from aerial images. There is a lot of literature by making small area estimates at the regional level for poverty. And a part of this literature is based on machine learning approaches that predict poverty from satellite or aerial images. And the mainstream literature, they train a machine learning algorithm on sample data and then apply this. They use the sample data to annotate images, train a model, and apply that model to all available images to predict poverty. And this is particularly popular for developing countries. Now, in the Netherlands, we have income and poverty statistics that come from a register. So we have a complete enumeration of poverty and income. And that gives us a unique data set to test this approach. So the purpose of our project here is to develop a deep learning algorithm to predict poverty. And now we can do all kinds of simulations with all kinds of different sample designs where we draw households from our registers and make estimates based on the samples and use only the sample estimates to annotate images, train a model, and then make predictions for the entire country, compare it with the known truth. And we also like to illustrate that it is better to use this as auxiliary information in a small area estimation model instead of ignoring the sample data and base the predictions only on the machine learning algorithm. Now, in the first attempt, we tried to predict poverty using 4 different types of images. We looked at images that are on a scale of 100 meters by 100 meters compared to images that are based on a scale of 500 by 500 meter. That are the 2 columns. But we also looked at 2 different spectral bands. We used the standard red, green, and blue band, which are the 2 images in the first row, and compare that with a near infrared band, which are the 2 images in the second row. Now we have disposable household income from all our households residing in the Netherlands. And for some strange reason, we got permission to attach or to match the geocodes of all these households to this complete enumeration. And that allows us to annotate all images with 3 different labels. The first label is there any inhabitation visible in an image? But we also created a label whether there is poverty in this image. So that means a 0-1 indicator, whether there is at least 1 household living under poverty. And we also attached the label that is the poverty rate. Now what we did, we developed a model that is based on a convolutional neural network. And we use the interception V3 model, which is 48 layers deep. We train the model by minimizing the negative log likelihood of a binomial distribution. And we evaluate our performance with the relative loss of the root mean and the root mean squared error with respect to random guessing. And in this case, random guessing is the fraction of the label that as we observed in the training set. And I'm very proud that we have at Statistics Netherlands this Formula 1 racing car that is really suitable to doing this kind of heavy computations. There's only one drawback. Formula 1 racing cars also require a lot of maintenance, and this machine is often not available because it is under maintenance. So therefore, I don't have very nice results to present here. But from a methodological point of view, the main difficulty here is to predict poverty. Poverty is not an object that you can see in an image. So that's the reason that we have 3 different prediction and 3 different prediction tasks. First of all, we look at inhabitation because that is a visible object in an image. And then in the next step, our training task is to predict poverty, given that there is inhabitation. And finally, we try to predict the poverty rate, given that there is poverty. I'll skip this one. I thought, yeah, machine learning people, they don't use formulas but pictures, and I tried to adapt to it, but yeah, let's skip it. Let's go to some early results. Here you see the results for inhabitation. Here you see the relative loss. So 1 means that you do, that is basically the level of random guessing. You see in the first column the results for the 100 by 100 squares. In the second column for the 500 by 500 squares. In the first row, you see the standard red, green, and blue band. And in the second row, you see the near infrared band. Now, predicting inhabitation, yeah, we're doing quite good. That's not a surprise because, yeah, what we basically predict is urbanization, and inhabitation is clearly strongly correlated with urbanization is clearly strongly related to inhabitation. So this are really good results. Now, predicting poverty, given that there is inhabitation, that's already more difficult. But yeah, here we perform better with the 500 by 500 squares. And the differences between near infrared and red, green, and blue is not very different. And finally, predicting the poverty rate, given that there is poverty, that is really a difficult prediction task. And there we do not really better than random guessing. Another result is that we looked at different sample sizes for predicting, in this case, inhabitation. So this is based on a sample of 100 images. These are the results based for 1,000 images, 10,000, and 100,000 images. And you see that with relative small sample sizes, and annotate only the images that are based on the small sample sizes, we can still do a good job for predicting inhabitation. You see some overfitting here in the very small sample sizes, but yeah, this is an encouraging result to use small samples to annotate a set of images and then train a machine learning algorithm and apply that to other areas. And so the first result is, well, we can do a good job for predicting inhabitation. We have reasonable results for predicting poverty given there is inhabitation, but predicting the rate is difficult. We have the best results for 500 by 500 meter images. We don't see any reason to use near infrared instead of red, green, and blue. And predicting inhabitation and poverty is also possible with small sample sizes. And yeah, this is recently published in this paper. Now, the ongoing work is to start simulations with different sample sizes. Well, what we currently do when our racing car is not under maintenance is to draw samples by using a two-stage sample. We draw small m out of capital M images. And then for these sampled images, we draw small n out of capital N households, construct direct estimates for poverty for these small m images, train then a convolutional neural network, do the prediction for all capital M images, and then make estimates that are based on the images only, which is the standard approach in mainstream literature. And we want to compare that if we, instead of using these predictions, use them as an auxiliary variable, for example, in a small area estimation model or an area level model, similar to what has been presented by Kyoto. Okay. Well, she proposed a similar nice approach yesterday. but yeah, the whole idea is we know the truth because we observe poverty and income in a complete enumeration, so we can compare it with the truth that comes from our tax registers. Well, to underline, it's understood that we do not use this to predict poverty in the Netherlands. We have a complete enumeration, and it is impossible to beat that approach with this approach. I'm going to skip this, but the last approach is that you can also use information, statistical information that is extracted with a machine learning algorithm from this kind of sensor data, for example. You can use that as additional auxiliary information to improve your sampling strategy. For example, by use it to draw samples to draw PPS samples proportional to this statistical information, or to use it as a stratification variable, or to include it as an auxiliary component in the regression estimator. But I'm going to skip that. So I tried to give an overview how you could use new data sources in official statistics. The first approach is a primary data source, but that requires generally a higher risk appetite because you don't have control over the availability of the data, the stability and the consistency of the data over time. You have to deal with selection bias, and most methods that are available in the literature to adjust for selection bias require structured data with strong auxiliary information, and that is basically only available in survey samples that are based on non-probability data, non-probability samples. So another way is to combine it as covariates in model-based inference procedures. That has the advantage that the primary data are still the design data, and its availability is still under control of the National Statistical Institute. And that is useful to produce more detailed or timely data with small area estimation methods or nowcast methods. I think, because most official statistics are based on repeated surveys, time series models are very appropriate to do this. I illustrated this with the monthly publications of our labor force survey. The last approach I skipped, but I think it speaks for itself. That was it. Thank you.
Thank you so much. That's amazing to see the innovation at CBS Netherlands. Because we started a bit late, we'll take 10 minutes or so questions and discussion.
Thank you, Jan. Very interesting. In the first example, you showed the nowcasting and using like the claimant counts and also the Google Trends. When you use the Google Trends, did you manage to use that also when you show the multivariate time series in domains? So you first showed just one time series and then the 6 for the 6 domains. Then when you plug the Google Trends, is it just like the same trend for all the domains, or you just ignore the domains in that model? Or have you found that the Google Trend is more similar to one of those 6 series? So in a sense, to try to understand whether the Google Trend can be more related to one of those domains, I don't know, younger people or older people, that's it.
With the Google Trends, we applied it only to the series at the national level. Sorry for that. We didn't apply it. We did not try to apply it to the 6 underlying domains. That's your question, huh? No. That results refer only to unemployment at national level. It was a PhD project and time was running out, and maybe a more important reason was that we think for the Netherlands, the claimant counts are beating, or the Google Trends will not further improve compared to the claimant counts that we have. So we decided to stop with that. But I think for countries that don't have this register, Google Trends can and will be a good alternative, because I also apply it with friends in Brazil. They don't have good claimant counts, and there we also observe that the Google Trends brings something additional to their labor force survey. Is that answering your question? Yeah. Okay. Thank you.
So first of all, thank you, and I beg your pardon because I was late. Anyhow, you have just told that machine learning can be used to improve design, sampling design, have I understood? Maybe if you can say something more on this, even if you have not presented in the slides, but also it is something very interesting to us. Thank you.
Yeah, I can, but
Can we get access back to the slides?
oh yeah, it would help. Yeah. Thank you. So we did a small exercise that comes from our innovation survey. This is a survey that publishes information about innovative companies. And that is a survey of 10,000 companies. And the well-known PDAS, he's also somewhere here. He developed a machine learning algorithm to predict innovative companies using texts that are scraped from websites. And he used basically this innovation survey to annotate the websites that he could get from the internet. So he developed a machine learning algorithm to classify these companies. And this is basically the probabilities that a company has innovative activities based on his machine learning algorithm. So you can think again, how can you use this information? You can use this primary data to predict the number of innovative companies. That's cost effective, but it requires a high risk appetite. For example, if you want to use the same model to future periods. And if I understood Pete correctly, and he can correct me when I'm wrong, he always faced the problem of what he called model drift, which implies that if you extrapolate the model to other periods, the performance weakens. So at some point, you could agree or admit that you always need survey data to update that machine learning algorithm. Well, you can put this information, instead of using it as the primary data source, also, again, in a small area level model, as discussed before. But you could also use it to improve the sampling strategy of the next upcoming period. For example, by drawing that sample proportion, using PPS sampling, where you use these predicted probabilities, or base your stratification based on this information, or to improve your Greg estimator. And I think that is also attractive for a National Statistical Institute, because then you're in an approach that has the lowest risk appetite, because you still have survey data as a primary data source. Your estimation procedures are still based on the well-known design-based inference approaches. And if this information has additional, if this auxiliary information has additional information, then it will reduce the variance of your Greg estimator or your Horowitz-Thompson estimator. And if it doesn't have any additional value, then it will not disturb the whole production of your official statistics. Now, the first results were not very impressive. So the whole method, Pete is still working on it. We compared it here with, we compared 5 estimators, where the first one is the Greg estimator. And then we compare it with the first one is the Horvitz-Thompson estimator. And we compare it with 4 Greg estimators that includes these probabilities, but also the number of websites and the language of the websites and both. For 4 different variables, here, you don't see much reduction in these sample estimates at this moment, but again, this is still ongoing work, so we hope that we can improve the whole of, not me, I'm not familiar with this kind of machine learning techniques, but I hope that Piet can still improve upon this approach, that it also contributes to, this way of using this auxiliary information. That's it. Okay.
Thank you.
Thanks for claiming additional presentation time.
Are there any other questions? Or we're anxious to go for a break? All right, thank you so much. And let's thank Jan van der Brakke, who came to give the masterclass. Sorry, what time do you want us back after the break?
We should be here again around 3:30.
Hello, everybody. Can we take your seats so we can start? So welcome to the afternoon session and the last session. So well done for sticking with us to the end. So we have in the session 4 new data sources for small area estimation. We have 2 invited talks, and then Giovanna will provide the discussion. And so the first paper is Bayesian small area estimation of origin destination matrix. And who's giving it? Who's giving the talk?
Fabrizio.
Fabrizio, okay, not you, because you didn't. And the second, controlling selection bias and non-probability sample using small area estimation application to official statistics. Francesca, nice to see you here. And so Fabrizio, the floor is yours. So each talk will be 25 minutes maximum, and then there'll be time for discussion.
Good afternoon to everyone. Okay, this presentation is about the estimation of the origin destination matrix. It's work done with a working group, so you can read a lot of names. And this work is for the publication, for the dissemination of the origin destination matrix at Istat. So the origin destination matrix can be viewed as a matrix in which the rows are the location of origin, the columns are the location of destination, and we have for each cell the commuting flow between the origin I and the destination J. And we have the number of locations for the columns and of course for the rows. So the problem in this case is quite different from the application we saw yesterday, in which the origin destination matrix was estimated only for one Italian region. Now we have to make an estimation for the whole country. So it is expected that most of the cells are null or with just a small quantity of flow. So we are dealing with an origin destination matrix that is a sparse matrix. Just few definition. We try similarly to what you saw yesterday. We try to describe this problem in terms of a small area estimation problem. In this case, the small areas are given by the pairs location I, location J. The target parameter is the work commuting rate, Mij, is given by the flows between the location of origin I and the location of destination J, divided, we chose the number of employed counts for the origin province I. It was also described yesterday, but I gave you again the definition of the work commuter adopted at Istat. This is a crucial point. So we consider as a work commuter any worker who travels daily back and forth from home and his workplace at least 3 times per week. And I told you that we are trying to estimate the metrics using small area estimation methods, and we use area level models, and in particular the Fayerot model. So the sampling model are of course given by the direct estimates, which are have known sampling variances Vij. The linking model is given by the relationship between the target parameter Mij and the set of auxiliary variables Xij. And the standard assumption for the random effects Uij are that are independent from each other, and they have a common variance sigma squared U. Okay, just some comments. I told you that the origin destination matrix is a sparse matrix. Then we have to take into account of this aspect. So both fixed and random effects have to be defined so that we have to we avoid to inflate the commuting flows between some cells, for some cells that are supposed to be empty or are supposed to have very poor commuting flows. For instance, the cells related to provinces that are very far from each other. And for the fixed effects, we have three types of fixed effect. Some auxiliary variables that is related to both the origin and the destination, that is related to the pair Ij, and the variable S and T, which are related to the origin S and to the destination J. So we have to put attention to variable of type S and T, because they can put some unexpected mass of flows of commuting flows for in provinces, in cells that correspond to provinces that are, for instance, very far from each other. And the same reasoning can be done for the intercept in the model specification. About the random effects, it is reasonable to have smaller null values of the random effect for some small areas, and higher values for other pair Ij. So maybe it could be that the standard assumption to have a constant variances for all the small areas could not be the optimal choice. For this reason, we try to implement two generalizations for the random effects. The first generalization is the spike and slab approach proposed by Dutton and Mandel, in which the variance of the random effects can be switched on or off depending on the value of the variable delta Ij. So for delta Ij equal to 1, the variance vanish. If delta is equal to 1, we have that the variance for the random effect Ij is the common variance sigma squared U. Alternatively, we can follow a global local approach proposed by Tang, Ghosh, and the other co-authors, in which the variance of the random effects can be adjusted by means of a tuning parameter lambda squared, so that each random effect can be small or larger depending on the value assumed by lambda squared. So in the first case, we have kind of an on-off switch. In this second case, we have a kind of dimmer switch, and we can adjust the intensity of the variance of the random effects. Since we are in Bayesian context, and since we are not able to elicitate informative priors, we prefer to adopt and to be in a non-informative setting. So we define, we use in our model specification weakly informative priors. So, for instance, for the regression coefficient of the linking model, we adopt a constant prior. For the common variance sigma squared u, we use an inverse gamma distribution. That is the standard option used in this case. We tried different values for the hyperparameters a and b. 10 to the minus 3, 10 to minus 3, 10 to minus 6, and 10 to minus 9. But we didn't find any relevant difference in the posterior distribution. So as we expected, there is no sensitivity to the hyperparameters specified in the inverse gamma distribution. Alternatively, we could use half Cauchy or half student distribution as proposed in Gelman in 2006. But in this case, there is the prior distribution proposed by Gelman are very useful when you have at least two level of hierarchy. We are in this setting just one level, so the inverse gamma just worked fine. And this is also in the paper by Chang, Data, and the other coders. They make a comparison between the performances of the inverse gamma and the half Cauchy half student, and they suggest to use the inverse gamma distributions. For the priors related to the spike and slab model, we use beta distribution for the probability that delta ij is equal to 1. We use the hyperparameters adopted by Data and Mandel, which is C equals to 1 and D equals to 4. That is, they put more probability mass close to 0 than close to 1. And to see if this can make some, this is relevant for the posterior distributions. We also tried a uniform distribution in 0, 1, and the beta distribution, which is the symmetric distribution used by Data and Mandels. That is to have the more probability mass close to 1 than close to 0. For the probability priors for the global local model, that is for the lambda squared ij, we adopted the same priors adopted by Tang, Ghosh, and the other co-authors. And on the first column, on the second column, you can have the expression of this prior, and on the first column, you have the name of the corresponding distribution of the random effect after marginalized over the parameter lambda squared ij. So we have for the random effects prior that correspond to the horseshoe distribution, the Stroder-Mamberger distribution, the normal exponential gamma distribution, the Laplace distribution, and the normal gamma distribution. All these prior have the propriety to put both probability mass close to 0 and far from 0. So they can help to data to choose if a random effect should be small or large. As auxiliary variables, we use the 2011 origin destination flows, the 2021 origin destination trajectories derived from administrative data, and also the distances between the location of origin I and the location of destination J. Okay, some observations. This is a different situations from what we saw yesterday. Yesterday we have true trips, but we didn't know if they correspond to commuter or not commuter. Here we know that a person is a worker, so potentially is a commuter, but we have that the administrative trajectories are only potentially commuting journeys. For instance, an individual living in Sicily can have signs of work in Venice, but maybe he's a smart worker and he does not travel, so he is not be considered a commuter. So the ability to detect from the administrative trajectories the true commuting trips can be played this role by the distance between the origin destination and the origin province and the destination province. And this variable, the distance, plays the same role played by the attrition attrition variable. That is, the larger is the distance, or the larger the cost to travel from I to J, and the less is the attraction between I and J. We also, so we try to adjust the admin data, the admin trajectory using a decay function depending on the distance between I and J. We use as a decay function the rate, so that is, we divided the administrative rate xij by the distance to the Q, and Q plays the role to control the rate of the decay. We try three different values for Q. Q equals to 0, 1, and 2. Of course, 0, there is no decay at all. 1 just divided by distance, and 2 divided by the square of distance. As an alternative, we thought to use this spline functions. Since it's not easy to find the optimal value of Q, we thought to use, for instance, xij divided by distance, and then use a spline function of this adjusted rate to correct for not proper specification of the value of Q. But this is still something that it's ongoing, so we have not result for this part. Okay, we have we tested different models, models from M1 to M6. The first 3 models are model with an intercept term. Model M4 to M6 has no an intercept term, and model M1 and M4 as auxiliary variables the commuting rate and the commuting trajectory. Model M2 and M5 have the the 2001 commuting rate and the 2021 commuting trajectory rate divided by distance. So we have applied Q equals to 1, and M3 and M6 have the same variables, but the decay rate is Q equals to 2. Some figures about the target parameters. I present some results for the work commuting flows from the provinces in the south of Italy. And we have 38 provinces in the south of Italy to all the other Italian provinces. So from provinces to south of Italy south of Italy to center and north. The overall number of in-sample small area is 323, while the overall number of out-of-sample small area is 3,743. And most of them are expected to be 0. As model diagnostics, we use standard criterion adopted for Bayesian models. So the deviance information criterion, the Watanabe Akaike information criterion. And to evaluate bias, we use the Bayesian p-value defined in a paper by Yu and Rao in 2002 and adopted by Fabrizi and other co-authors in 2011. And this diagnostic evaluates the probability of the posterior mean to be larger than the corresponding direct estimate. So in absence of bias of the posterior mean, the expected value of the Bayesian p-value, of course, is 0.5. And we also adopted another diagnostic often used for the evaluation of bias in small area estimation setting, that is the criterion proposed in a paper by Brown, Chambers, Eddy, and so on. And just to make an ordinary least square between the direct estimates and the model-based estimates. So in this case, in absence of bias, the regression line should be close to the 0-1 line. About the MCMC procedure, we have that all the posteriors are proper. Since we can sample from all the conditional posterior distributions, we could use simple Gibbs sampling to generate random sample from the posterior distribution. The number of chains is 4 for each model. The chain length is 1,000 replications. 1,100 replication, 100,000 replication. The number of Bernini is 500,000, and the thin is 10. That is that from replication to 500,000, 1 to 100,000, we just we discarded 9 out of 10 random draws to avoid autocorrelation of the random samples. The model was divided in 2 separate processes. An intra-provincial flows estimation and an inter-provincial flows estimation. So the first model is just to estimate the flows of people living in Naples and working inside the province of Naples. But this is much easier than the second problem, so I just want to put a focus on the second problem, since the first problem is just dominated by the direct estimates, so it's quite simple to estimate, to analyze, and so on. As expected, the models having an intercept term slightly outperform the corresponding models without the intercept terms. But we prefer to choose a model without an intercept term to avoid to put mass for a pair of provinces which are far from each other, and for which we expect to have null or very poor commuting flow. These allow us to have, and this is true also for a pair of provinces for which to have zero estimates for a pair of provinces for which both 2011 data and 2021 administrative trajectory rates are equals to 0. And here are some results. The chosen model is the model M5, which has no intercept, and we have the commuting rate at 2011 census and the 2021 commuting trajectory rate divided by the distance. So the first comment is in terms of the bias diagnostic by Brown, Chambers, Eddy. They all have very, very good performances. In terms of DIC, the best performances are achieved by the Spikens Lab model, while in terms of Watanabe archaic information criteria, the global local model with the Strodemann-Berger prior for the local parameters gave the best results. And both the Spikens Lab models and the global local models outperform the Fayerot model and the synthetic model. Now we can have a look at the some plots about the random effects. The first plot on the top left are the random effects of the Fayerot model, and the other from the second and the third on the first line and the other on the bottom are the random effects for the global local prior distribution for the other for the global local models. And we can see that the random effects for the Fayerot model are closer to 0 than as expected than the random effect distribution for the global local setting. Here we make a comparison. It looks strange, but it's the true plot. It's just a comparison between the random effect distribution of the Fayerot model and the random effects in the Spikens Lab model. We have a huge spike in correspondence of the 0 value. This is not bad. We also I remember that I told you that we want to test these priors for the probability for the Spikens Lab model, the probability that the variable delta, the switch on off, is equal to 1, and these are the results for the beta 1,4 prior. These are the results for the uniform prior for the parameter P. And the last one is the results for the prior distribution that put much more mass on close to 1 than close to 0. So we didn't find any relevant differences from one prior setting to the other one. So there is no large sensitivity to the prior choice. Okay, final comments. The 2011 census information resulted to be much more predictive than the 2021 administrative information, similarly to what we saw yesterday about the 2011 census and MNL data. The Spike and Lab model activates the random effects only when it was considered necessary. So their estimates are quite close to the estimates provided by the synthetic model. And for this reason, we can group all the models into some sort of groups. So we have the synthetic estimator, the Spike and Lab, Fay-Harriott. Then we have the global local model. And we could see that we have slight, just as low, and not a small difference between the first three setting and the last two settings, but because they use a different family prior. So we can put all the global local model all together, or just make a distinction depending on which family of prior they are using. Some words about future works. We want to adjust the admin data using spline functions. Maybe it would be important not have negative estimates then have to be adjusted, to use an unmatched linking model to prevent to have negative estimates, or use alternative sampling distribution for the direct estimates. For instance, beta distribution instead of normal distribution. This is some references, and it's over. Thank you.
Thank you. Shall we move on to the second paper?
Okay, thank you very much for the invitation. And today I will present a joint work on which many people of academia and National Statistical Institute have collaborated, as you can see here from the list of the authors of this work, who are Gaia Bertarelli from University of Venice, Nicola Salvati, Stefano Marchetti from University of Pisa, from my same department, and Donato Summa from Istat, Monica Scannapieco, that was formerly at Istat, and Monica Pratesi, that from both Istat and University of Pisa. This work is supported by several European and Italian projects. But the aim of this work, under a methodological point of view, is to propose an approach to correct for the bias when we use non-probability sample, when the aim is to estimate a given target parameter for unplanned domains. In particular, in this work, we extend two previous work of Kim to propose at the end a double robust estimator for estimating a given parameter at small area level. Under an application point of view, our aim is to estimate the proportion of Italian enterprise that are sensitive to SDGs at provincial level in Italy that correspond to NUTS3 level. This is the overview of my presentation. After the introduction of the problem, I will present the data, and then I will show you the method that we have developed, and then I present the result under simulation scenarios, and finally I show you the application result. Okay, we focus on estimate the proportion, as I have already said, of Italian enterprise sensitive or sustainable development goals, because this is an important topic that for a National Statistical Institute across all Europe. So we focus on a particular variable that we define, we call SDG enterprise sensitiveness. And we think that have information at this at the small territorial level, in particular for Italy at provincial level, is important for policymakers to implement well-targeted policies. However, the problem is that this variable is not directly measurable by traditional surveys on enterprises implemented by Istat. For this reason, we use a non-probability sample, a big data sample that is obtained through online web scraping. But as we already know, the problem is that if we use a non-probability sample, the estimation of a given parameter is biased. For this reason, to correct the bias, we embrace a data integration approach, and we need to use a probability sample to correct for this bias. But when the aim is to estimate a parameter at for small areas, here we have another problem when we use a probabilistic sample, because we have a small sample for the areas of interest. Okay, our target population is represented by all the Italian enterprises with more than 10 employees, and we select just the Italian enterprises in these four economic sectors: manufacturing, industry, wholesale and retail, trade, and other service activities. Our target population is in the Italian Statistical Business Register. And from this register, we select the enterprise with a valid website, because not all the enterprises in the register have an enterprise website, sorry. So at the end, we have a subset that we call B, and B is our non-probabilistic sample. Because from the set of enterprises in B, we scrape the website and we select some SDG-related words to build our target variable. At the end, our target variable is obtained by employing machine learning technique by using the words, the SDG words related. So at the end, we have in this big data sample a binary variable that is our target variable, that is equal to 1 if the enterprise is sensitive to sustainable goals, or 0 if it is not sensible. So this is our target variable, and at the end, in the B dataset, in our non-probabilistic dataset, we have this target variable with other variables like the number of employee of the enterprise average over the years, the turnover volume indicators, the sector, and other characteristics. Our big data is composed by more than 50,000 observations. As I already introduced, we need a probabilistic sample. In this case, the probabilistic sample that we denoted by A is the Istat special survey on enterprise perspective after the COVID-19 emergency. Also from this probabilistic sample, we select the same that enterprise with 10 or more employee in the 4 considered sectors. And we have a data set of about 20,000 observations. I remind you that our target, the target populations are the population in the NUTS3, the provinces in Italy. And the problem by using this probabilistic sample is that the sample size in some provinces is not so big. Indeed, for 35% of the provinces, we have less than 100 enterprises. So it's important, this is already, it's important to say that in the probabilistic sample, we know we have an indicator variable that denotes if the website, the URL is available or not. So from the probabilistic sample, we know that if an enterprise is in the non-probabilistic sample or not. So at the end, we have two datasets, two datasets, A and B, that share some variables: the number of employees, the turnover volume indicator, the code, the sector, the code of the sector, and some other geographical general detail. Our target variable is available in the big data, but is not available in the survey data. Okay, this is our the data that we have. Now I want to present you the methodology that we have developed to estimate, to correct for the bias when we estimate our target variable by using the non-probabilistic sample at the small area level. Okay, just some notation. Maybe it's already clear because today some other speakers explained this, but just to remind you what we are talking about. We have a target population, and this target population is divided into non-overlapping areas. And we have a non-probabilistic sample and a probabilistic sample. A non-probability sample, the size of the non-probability sample B is NB, and BI is the non-probability sample in the area I, and of course NBI is the sample size in that area I. And we have an indicator of inclusion, that IJ, that is equal to 1 if the unit J is in BI and 0 otherwise. So the non-probability sample contains the target variable and a series of auxiliary variables that we denote with X. We have also a probability sample A, and in this probability sample we know the inclusion probability of the unit J within the area I, so we know the sampling weights. Of course, the sample size in the area AI could be small, and the survey data do not contain the variable of interest, but contain the covariates, the same covariates that are in the big data non-probabilistic sample, and also the indicator of inclusion. So our target parameters are the area means. And I recall you, we have a binary variable. And by using sample B, we can obtain the estimate of theta I in the estimation of the area means by using a so-called naive direct estimator. If we use the non-probability sample, we can obtain the our target. We estimate the target parameter by a naive direct estimator. But even if the non-probabilistic data have a larger sample size, we do not know the sample inclusion mechanism, so the big data cannot be represent the target population. So essentially, this could be biased. So, as I have already introduced, we embrace a data integration approach to reduce the bias of the non-probabilistic sample by combining a probability and non-probability sample through a vector of common auxiliary variables. We have two, I would say, common assumptions. The first one is that we can observe the big data sample inclusion indicator in sample A, as already explained before. And the other, I would say, a common assumption is that the selection mechanism of the big data sample is ignorable. So, as you can see here from the definition of this selection mechanism, we have more, in addition to the covariate X, we have UI, that is a vector of area-specific random effect that characterize the between area differences in the distribution of the target variable given the auxiliary variables. So to develop our double robust estimator, we need to estimate the propensity scores. We use the data from the probabilistic sample to estimate the propensity score in the non-probabilistic sample. Usually, the propensity scores are estimated by employing a generalized linear model with a logit link function. In this case, we know that the population is a hierarchical population. So we decide to estimate the propensity score by employing a generalized linear mixed model with a logit link function. In other words, we include in the estimation a vector of area-specific random effects. So we use the data from A. We also include sampling weights in the model estimation, and we obtain an estimation of the fixed and random effects. Okay, it could be noted that even if the area-specific sample size is small, because we know that we assume and we know in the application that the sample size in the areas could be small, when we estimate the propensities, we borrow strength from the whole sample, so the estimation of P is stable. So as second step, we need to use the data from probabilistic sample to predict our target variable. And also in this case, we use a generalized linear mixed model, because the same idea, we have a population that is divided into areas. So we consider the hierarchy of this population in the estimation procedure. So here in this formula, H is the link function that is in our application, will be also for this outcome model a logit link function, because our target variable is a binary one. And but it's okay, this is a general formula for also when we have count or continuous target variables. And here gamma I is the vector of random effects. So we use generalized, as I already say, we use generalized linear mixed model. We obtain estimation, maximum likelihood estimation of beta and gamma. So at the end, we can develop our double robust estimator, where the first for estimate the mean of theta in each area. The first part of this estimator is a sum over the unit in the non-probabilistic sample, then where we have done a sort of correction, of course, by using the propensities. And in the second part, we have a sum over the units in the probabilistic sample, and we consider here also the sampling weights. This estimator is double robust, and because it's consistent if the model for propensity score or the model for the study variable are correctly specified. We have proved this in the paper. Okay, when we are in the small area estimation framework, an important part is to estimate the variability of the estimator. At the moment, we have just a resampling and a bootstrap procedure to estimate the variance of the estimator. In particular, we propose the following bootstrap variance estimation. And the first step, we consider the sampling design of the probabilistic sample to obtain bootstrap replicate of A. In the second step, we do not know the sample design of B, of course, so we employ a simple random sampling with replacement from B to obtain B star, our bootstrap replicate of B. And then we obtain the propensity score, the bootstrap propensity score, and we fit the model on the bootstrap sample to obtain estimation of the beta and the area-specific random effects. At the end, we obtain our bootstrap double robust estimator, and we can compute easily the variance. It should be noted that this is a very simple bootstrap, but we have tried other bootstrap approach like the Antal-Tillier proposal and also parametric bootstrap, but the results of this one are better than the others, so we have decided to present the result of this bootstrap procedure. Okay, now I want to show you the result by using simulations. And this is a limited simulation study, and that we use this to compare the small area estimation double robust estimator, this one, with the naive one. So where the naive one is just the mean by using the non-probabilistic sample data. And also we check the validity of the variance estimator. Okay, also in this case, we have a binary variable as target variable, and we generate this variable under a linear model and a non-linear model. And we have two auxiliary variables and a vector of random effects. Here we have listed how we generate the x1 and x2. The first one is a normal variable. The second one is a non-uniform. We have 100 small areas, and in each small area we have just 10. We select just 10 observations. The big data sample inclusion indicator was generated under a Bernoulli with P with parameter P, where this parameter P is calculated by using a linear model and a non-linear model. In this case, to calculate P, we use just a variable that is x2. Okay, combining this two model for the outcome and the two model for the propensity, we have 4 scenarios. The first one, the outcome regression and the big data propensity score model are both linear. In the second one, we have the outcome regression model is linear, while the big data is non-linear. The opposite in the third scenario, while in the fourth scenario, both models are not linear. The parameter of interest was the population proportion in each area. We obtained this small area double robust estimator by employing a random intercept logistic model as the working propensity score model by using just the x2 variable, while we use the following model for the outcome. So at the end, we test our estimator also in the presence of misspecification, because if you remember, in the 3 last scenarios, we have a misspecification of the model, the misspecification of the outcome, of the propensity, of the outcome model, and of both model in the last one. We compare the two estimators, the double robust and the naive estimator in terms of relative bias and mean-square error. And here's some results. As you can see, the naive direct estimator is essentially biased in all scenarios. We have a positive bias in the scenario 1 and 3, while the bias is negative in the in the second one and in the 4. While if we look at the result of our estimator, we have essentially no bias. So at the end, it seems that our estimator correct for the bias of the direct ones. In terms of mean-square error, the difference are negligible. Even if as expected, we have a slight better result for the naive one. Okay, in terms of also in terms of the variance estimator, it seems that we have pretty good results. And now I move to present the result of our application. On the left, you have we plot the result by using the double robust estimator, and on the right by using the naive direct estimator. As you can see, the overall pattern is more or less similar between the two maps, but we know that the direct estimator is biased, so policymaker, if you use this data, could be implement, for instance, not so well targeted policies. So our estimator, it's better, as you can see in simulation scenario, because it's correct for the bias. There is a north-south divided as expected. The enterprises in the north are more sensitive to sustainable development goal, but there are some exceptions here. For instance, the province of Vibo Valentia in Calabria. And also in terms of coefficient of variation, the results are quite good. Okay, to conclude, that at the moment, this is one of the first attempts to obtain a reliable estimate from a non-probability sample at the small area level, and the results are quite good, because this proposal tends to reduce the selection bias. However, there are some open cons of the proposed approach, because we need a probabilistic survey to correct for the bias. The indicator of inclusion should be known in the probabilistic survey, and this can be reduce the number of possible applications. And at the moment, we have just an approximation of the we have a bootstrap approximation of the variance. And in the application, of course, we have an is not related with the proposed bias correction method, but in the application, our target variable is estimate via machine learning and is sensitive to the words that we use. So this is some references, and thank you very much.
Thank you very much. And now we invite Giovanni for the discussion.
Yes, thank you, Natalie. Thank you to the speakers for two very interesting talks. So this is the outline of my discussion. I will just give a brief overview of the two papers and then some suggestions to each of the two. The two papers have similarities and differences. The similarities that I would say that they use small area estimation methods for non-standard small area estimation inferential problems. So this is not like the classical small area estimation. And we're discussing about small areas, but there are a large number of authors, and Marco Dizio brought this out yesterday as well. So it really means that when you try to include these non-standard sources of data, you do need a lot of different skills. And the difference is that other than using a Bayesian versus a frequentist approach, there are really two different papers in their stage of maturity. So the first one is a very much work in progress, where the second one is essentially a published paper. So my discussion has very two different levels. So the first one, Fabrizio. So the inferential target, we have the origin destination metrics, so MIJ. Rows are origin location and columns are the destinations. And so the number of counts of commuters is just like given by the overall number of employed individuals in location I times the commuting rates. And in this paper, the target parameter of interest are these commuting rates MIJ. So it's a sparse problem. Indeed, at first I thought it wasn't really a sparse problem compared to the municipality level, but it is. And so the small areas here are the cells, IJ, Italian provinces. So overall, we would have like 107 by 107 metrics, but in the application, we just look at one macro region, so 38 by 107. So the survey data comes from the permanent census, and the auxiliary data has two sources. The first one is QIJ, is the number of potential commuting journeys, and the potential commuting journeys come from tax registers. And since we are interested in commuting rates, it's included in the model as the rates of potential commuting journeys. And then we have previous values on commuting rates from the 2011 census, which was the last full enumerated census in Italy. So the modeling approach is, it would just use like a classical Fay-Harriot area level model. But here, the assumption of a common variance sigma squared u should be relaxed. And one way in which this is proposed by using Speiken's lab, in which the sigma u is pre-multiplied by this delta ij, and delta ij is just Bernoulli random variable with probability theta. And the other one is the global local, in which sigma u is pre-multiplied by this local parameter lambda ij, and you actually tune this parameter by using different choices of priors. Now, the ability of QIJ, so the auxiliary information from the administrative data to detect true commuters, is a function of the distance, of course, between origin and destination. And for this reason, this quantity is included in the model after being divided by the distance. And so we saw, sorry, maybe Fabrizio used Q, I used P. So by choosing P equal to 0, 1, and 2. And then another proposal is that the effect of zeta could be modeled by splines. This is just in the papers, but as we saw, it's not in the application. So some suggestions, ideas. So the first one was already in the conclusion. So as it often happens in discussions. So my first idea was we are using a Gaussian assumption for commuting rates, and which can also be small. And so I would propose to test for transformations that you usually use for Fayariot, but moving to a beta would be even better. And then just an overall question would be, what about modeling counts directly? Or why would you decide to model rates instead of counts, maybe by directly accounting for the constraint that the sum is equal to Ni, and you do know a capital Ni? It's just a question. Now, in the need of setting many random effects to 0 because of the sparsity of the problem, the first thing you can think of is lasso or spike and slab lasso. And so question, have you thought about that? And then in spike and slab, I'm not an expert, but I was wondering whether you could have like the probability of the delta ij being equal to 1 or to 0, of course, to depend on the distance, because essentially you want to just set the random effect to 0 as the distance increases. So you may have this quantity directly depending on the distance. And then there's a different approach that you can consider, is to relax the common sigma squared u and also a common beta. So in a sense, to try to model this extra heterogeneity, you can try to think of a mixture model in which your mij's, given covariates, and given the fact that ij, so the location ij belongs to a group, so you actually have like different Fayariot models in a sense. So you have all your cells divided into groups, and for each group, you estimate a separate set of regression coefficient and a separate set of sigma square c. And these groups would be estimated from the data. You could call them group clusters, latent classes. And the probability of a location to belong to one group can depend on covariates. So in a sense, you can have for some groups, so for some cells, a different value of the coefficient and of the sigmas. And then in case you pursue further the use of p-splines, then my experience says that you may want to use what is called the Daimler-Reich orthogonalization for the metrics in which you plug the bases, because in the Bayesian approach, this is really fundamental to help a proper mixing of the chains, but this is my experience. And then the second paper. So as Francesco very clearly illustrated, they're trying to estimate the proportion of Italian enterprises that are sensitive to SDGs. And the main issue is here to have a bias correction of the estimates from a non-probability sample for small domains and using a probability sample. So as I said, this is not a real small area estimation problem, because in the sense the target variable comes only from the big data source B, but the domains are small in the probability sample A. So here you need a model to adjust for the bias, not really to reduce the variance. And they propose to use a doubly robust approach, so inverse probability weighting plus mass imputation. And they assume that the selection mechanism is ignorable, and they use, I would say, a safe flavor. So they use a smaller estimation approach in both models. So both to model the probability, the propensity of being in the big data source, and both to model the mass imputation model. And when I say safe flavor, I mean that there are random intercepts in both models. So if I were a referee, so since the paper is published, so there isn't really much room for improvement, I would just ask, since you had a binary target variable, why did you use a naive approach in which you just use your logistic regression model and plug in your beta hat instead of using an EBP, so an empirical best prediction, which is the predictive power of the predictors for both models. The more I look into these applications, the more I understand that it's so important, because if you have a bad model, you cannot just do much. And is it comparable to that in the simulations? Because in the simulations, everything seems to work very well, but then it really depends on how good are the predictors compared to those that you use in the simulations. Then maybe this is not the issue here, but I think that it's maybe an important topic. So here, maybe say you have small NBIs. So you don't not only have like, it's not small in the probability sample, but it's small in your big data. Maybe it's not relevant, but I have an application soon. And so if you use inverse probability weighting for areas that are small, also in the big data source, then you're introducing some extra variability because you're weighting there. And I don't know if it's an issue in your application, or if you thought about this, or if it's an issue anyway. And then in the simulations, you just compare like the naive and the doubly robust. It would have been interesting to disentangle the two. So the role of IPW and of mass imputation. So I would have just liked to see the performance of mass imputation only and of IPV only, and see what it was. And so the bootstrap, I think that really the bootstrap can be where something can be done. And so at step one, you say that the sample, because here you need to find a bootstrap that allows you to account for both the model-based and the design-based variance. So the step one tries to estimate the design-based one. And for this reason, you say you need to extract a sample from sample A using inclusion probabilities. In the end, what you really need is that in step one, you need to follow the standard practice in survey sampling on creating replication weights for design-based variance estimation. So you really need to be as close as possible to the original design for the enterprises. And maybe you can just use what is very common as StatsCan, like the RAUVU bootstrap or unaffiliated population bootstraps. So it wasn't very clear you said something in the talk, it wasn't very clear from the paper. So how was this first step one performed? And then the second step, maybe here, I was wondering, why did you use simple random sampling? Because in the sense, the second step tries to mimic the selection from the known probability sample. And it's true that you don't know that, but in a sense, I'm not sure that just using simple random sample is enough to account for the fact that you do have an unequal selection for your big data. And the proposal in the paper, which is very close to the proposal in the Kim paper, I think was, but maybe I'm mistaken, I think it was proposed for a method that was just looking at mass imputation. So simple random sample was okay because it was just looking at mass imputation. But since here you are looking at doubly robust, I think that you need to do more than just step 3, in which you re-estimate your probabilities to account really for IPW. In a sense, I think it's like, maybe we can learn something for all the literature on non-response. You essentially have a Poisson sampling in which you have estimated your probabilities. But this is really open for a better bootstrap, as you said. And so my final slide is that, so the title of this session was New Data Sources for Smaller Estimation. But I think that the last paper and many of the things that we've heard in the past 2 days, and I was also thinking of Jan presentation and the work that he described briefly after Monica's question, is that maybe we will see more and more papers on how smaller estimation can be useful for new data sources, because all the machinery that we've learned so far of smaller estimation can really be used to get a better mass imputation for these new data sources that really account, for example, for domains or planet or unplanet domains. So thank you.
Thank you very much for such insightful comments. It's always nice to have Giovanna discussant, isn't it? Do you want to comment?
Joanna, please, can you go back to the slide?
My slides or
Yeah.
yours? Mine? Rimettili su, vai. Queste?
The slide with okay. Okay, first of all, thank you for your insightful comments and suggestions. I start from the last one. Yeah, we encountered some problems in have a good mixing of MCMC chains. So we will try for sure your what you suggested us. So thank you a lot for this comment. And about your proposal to model directly counts and not rates. Yeah, we talked about a lot on this point. We were afraid that modeling counts, we had the more that more large pair of provinces could in some sort of just drag all the relationship between all the other pairs that are smaller. But we can try it and we can see if it's better or not. So why
It was just to
not?
avoid very
Yeah.
small numbers, because with rates, you may end up at very,
Yeah.
very small numbers, but
Yeah, on the contrary, we had the just the opposite problems. We have just small rates. So probably, in fact, one of my comment on the last slide is similar to yours, and just to use non-linked different linking models. So just to take into account of transformation of the origin variables, the original variables. So this is for sure something that we have to do. So in order to have small random effects, so random effects that are close to zero, and yeah, of course, we can also apply lasso or spike and slab or spike and slab lasso. It's I think it should be a good idea, and just not to make simple spike and slab. And just since we are talking about spike and slab, it's very useful and correct your suggestion to model the probability of the variable delta to be dependent from the distance, because one of the main problem that non-sample areas are some sort of different population from the sample one. So and the difference depending on the distances. So just including the distances also in the modeling the probability, I'm sure that is the right choice. So I agree with your comment. And yeah, okay. But
Yes, thank you, Joanna, for your very insightful comment. Maybe I can start from the bootstrap. Yeah, in the first step, we try to replicate, in some sense, the same sampling design of the survey that we And we have, honestly, what we have done is to follow the referee comment to implement this bootstrap and in order to satisfy his request. So at the end, this is the honest answer. But yeah, we know that this is not a very good bootstrap, I would say, but we have tried many, maybe not your, we don't follow your second comment, but we have tried many bootstrap approach. This is one that give us the best result and the one that satisfy the referee. So we have proposed this. It's honest, but it's this is regarding the other comments. Yeah, you can. If I understand correctly, the first one, you think we can use the BP in the non-probabilistic data to estimate the...
In the mass imputation, you run a logistic mixed model. Then you estimate beta and U, and you
Yes.
just predicted your 0, 1 using like X beta hat. Yeah, and that's just naive. You just plug in. It's not really the empirical best prediction approach that you would use, like the Jiang approach.
Yeah, okay. Yeah, yeah, maybe this is a good point, but we don't consider the ABP. Yeah, we just use a mixed random effects model to replicate a sort of small area estimation model, traditional small area estimation model. Yeah, we have tried other different model in the application to test the predictive power of the predictor. It seems that it's I don't remember the R square or the measure, but it was a good. Yeah, it's fine. Okay, we also test this difference only and of IP. We have in the paper we put this and the result. This is the EPW. It makes sense to add this in the estimator because its role it's important at the end.
Okay, I'm afraid we don't have time for questions. We're already way over time here. So let's thank the speakers so much. And thank you for hosting the IASS today. And please join the IASS.
Okay, so we are at the end of this workshop. I will take only 10 minutes of your attention to close this third edition of this workshop on methodologies in official statistics. I think that this year we have had really high-level contributions and discussions. So I hope and I think that this has been really an important occasion for discussing and exchanging ideas among researchers from national statistical institutes and from academia, as it happened actually during these 2 days. This year, the workshop focused on some very relevant areas of methodological research for NSIs, relating to opportunities and challenges opened up by the combined use of survey and non-survey, usually non-probabilistic data sources for produce the so-called multi-source official statistics. In effect, the accessibility to new sources and the possibility of exchanging and reusing data have opened up complex and frontier methodological perspectives with the need of progressively redesign the way in which data are collected, treated, analyzed, and interpreted, making use of emerging methodological approaches, including data science and artificial intelligence, in combination with standard inferential approaches with many expected benefits, for example, in terms of reducing cost and burden on respondents, but also with new and complex issues to solve. Yesterday, in the first session, we started analyzing challenges derived from the integrated use of traditional and non-traditional data sources, such as administrative data and big data, into a, let's say, unified statistical framework. The multi-source approach to official statistics is very attractive for NSIs due to its associated opportunities and expected benefits in terms of ensuring comprehensive, accurate, relevant pictures of complex phenomena as are those that we investigate in NSIs. This approach ensures, for example, that gaps, inconsistencies, or inaccuracies affecting individual data sets can be addressed, and it allows for broader coverage of populations or domains that might be underrepresented in traditional surveys. As said, multi-source statistics also present challenges, such as the need of developing advanced methods for data integration to ensure effective linkage between sources, but also to address privacy concerns. We need also to develop common metadata standards to ensure consistency and usability across datasets. And of course, we need new or additional criteria and methods to assess quality. As most of multi-source statistics are based on the use of non-probabilistic data sources, which is a topic that crossed all the sessions of this workshop, additional key challenges must be dealt with, such as bias and representativeness. In this context, advanced methods are required to adjust for biases like calibration, data integration, exploiting auxiliary information from reliable probabilistic sources. Also, propensity score matching for dealing with selection bias is an option. However, additional research is needed for using these and other methods in complex situations like those in official statistics. In the third session this morning, we discussed about data science, and official statistics, which are topics increasingly interconnected as data science brings advanced tools, methods, and technologies to the traditional processes carried out by official statistics that requires to be further analyzed and tested, as they could transform to some extent the way in which official statistics are produced. In fact, data science introduced machine learning, artificial intelligence, predictive modeling, which enables statisticians to extract deeper insights from data. While traditional statistical methods rely on structural data sets, data science enables the processing and integration of unstructured data, such as sensor data, satellite imagery, and web data. In addition, data science allows for the automation of repetitive tasks such as data editing, data prediction, validation, and reporting, allowing to release resources for other analytical work. Challenges in this area rely, for example, in the need of filling the existing skill gaps, and this has been discussed also today, for example, by training statisticians in programming, machine learning, and advanced analytics, and in ensuring the methodological transparency and reproducibility of methods, as artificial intelligence and machine learning models, as we well know, can sometimes operate as black boxes, while these quality dimensions are fundamental for official statistics. Advantages and risks associated to the integration of data science methods into traditional inferential approaches have been discussed also this morning, and we all recognize that further research is needed, as data science can support, in several sense, official statistics in remaining relevant, enhancing their utility, and better serve stakeholders. Actually, in this morning's session, it was also discussed an important topic which represents a fundamental element for official statistics, the evaluation and representation of uncertainty in the disseminated statistical figures. This aspect is even more relevant when dealing with multi-source statistics and non-traditional and non-probabilistic data sources, because traditional techniques and frameworks need the revision to cope with the sources of uncertainty related to these new production approaches. Actually, uncertainty is not anymore mainly dominated by sampling errors, but other errors become influent and consequently should be measured. For instance, uncertainty due to lack of information on the hypothetical data generation model for non-probability samples, and uncertainty of predictions with complex models, including machine learning methods. This area has an increasing importance, and again, it requires research investments to make the underlying theories effectively applicable to official statistics. So the last session of the workshop, the just finished session on small error estimation for new data sources, has been devoted to the use of small error estimation in official statistics in presence of new data sources. We can say that much progress has been made since the first applications of this type of models for statistical estimation, and the situation, of course, has changed enormously in last decades. There now exists a wide range of different, often complex models that can be used depending on the nature of the measurement of the small error estimate and, in particular, on the auxiliary data which are available. It is important to remind that some authors underline the need to have a global strategy aimed at addressing the problem of estimation for small areas already in the design phase. In other words, it is necessary to adopt measures aimed at improving the estimates for more domains right from the planning and implementation phase of the sample design and estimators. Naturally, this global strategy must also be extended to the case of multi-source integration processes, also including the use of non-probabilistic data sources. Actually, the current research aims at enhancing these methods in the context of multi-source integration, and emerging themes concern, for example, the exploitation of non-probabilistic samples together with data from sample surveys. So I'm going to conclude. I want to conclude reminding that in a continuously evolving data ecosystem, also NSIs have to evolve in order to maintain their central role in ensuring reliable and high-quality statistics, maintaining high methodological standards and commitment to privacy in compliance with the principles that regulate official statistics. As for Istat, I can say that the strategy is to continue investing in methodological research to progressively complete the modernization process started some years ago, moving towards multi-source production processes to ensure more efficient and possibly even more consistent and reliable official statistics. One of the most relevant initiatives in this perspective is the Integrated Census and Social Survey System project, also presented yesterday in one of the workshop sessions, where a systemic approach in the design and methodology of population censuses and social surveys, from sampling design to estimation, is being proposed here at Istat, also leveraging information from the Istat integrated system of statistical registers, of course. This profound innovation aims not only to increase the overall consistency and efficiency of the system of social statistics, but also to address the declining response rates affecting socio-demographic surveys in Italy and also in other countries. We will also continue investing on research for the use of non-probabilistic data sources to support the production of official statistics, of course, also participating in research activities of European and international projects, as you have also seen during these 2 days. Given that, what is extremely important for us at Istat is to continue collaborating on all these topics with academia at the national and international level, and with other NSIs, especially at European level. As you know, Eurostat is having a key role in supporting NSIs in developing methodological research in all the areas discussed during this workshop. Therefore, I want to underline again that events like this workshop are of paramount importance for us, and I think also for other NSIs, in order to ensure the scientific quality of methods and approaches for official statistics. Before concluding, on behalf of Istat, I would like to thank again the now legendary coordinator of the Istat Advisory Committee on Statistical Methods, Professor Daniela Cocchi. And many thanks to all of the committee members, Professor Giovanna Ranalli, Li Chung Zhang, Brunero Eliseo, Marco Alfò is missing, but okay. David Aziza, Pete Das, Piero Falorzi, and Natalie Shlomo, who participated also as president of the International Association of Survey Statisticians, and many thanks for that. Many thanks to them for their really valuable advice on Istat research work and for their very stimulating discussions during this workshop. Many thanks again to Professors Pfefferman, Kim, Tillet, and Van der Brakel for their willingness to participate in this workshop and for their thorough and comprehensive master classes. And of course, many thanks to all the speakers from Istat, from the academia, and from other NSIs who contributed to the various sessions. Thank you very much. Last but not last, I want to extend special thanks to the members of the Istat Program Committee for their enormous job in preparing the scientific part of the workshop, but also managing organizational aspects such as microphones, security, presentations, and so on. So thank you very much. And special thanks also to the Istat communication and IT teams for the excellent organization and technical support. Last thanks is for you, to all of you for attending this workshop, either in presence and online, and see you next year for the 4th edition of this event, again here in Istat.